Hi everyone, this is discussion section 12 for CBE40. We'll be talking about flash drums today. I'm going to keep this discussion pretty short, just sort of get you the essentials of what you need to solve your homework this week. So this is actually our last normal discussion section. We'll be doing review session videos for the next discussion sections, but this is the last discussion section of sort of new content. New being you've seen all of this in lecture, and so great. Okay, so before we get started into the material, I just wanted to spend a little bit of time on logistics. So Dr. Siston's lecture from this morning, which was kind of some review stuff about TXY and PXY diagrams, which is what we'll be talking about today, but also kind of a preview into the kinds of problems you'll be solving in your future chemistry classes. One note I wanted to make on that, and Dr. Siston talked about this morning, is really pay attention in your math classes, especially when you do differential equations. I definitely remember as an undergrad, I had to take differential equations, sort of thought there's no way that I'll ever need this. I just need to survive this class. And then once I got to some of the higher level chemistry classes, I really needed that foundation and background in differential equation solving. So don't take that class lightly. You will regret it if you do. I definitely regretted it. And as you guys already know, but just as a reminder, we have participation points for both lecture and discussion. So there's an assignment posted for the lecture this morning that is just sort of a quick brainstorming response that you can do as you're watching the lecture. And there will be an assignment posted for this discussion section as well, which as usual will just be a really quick to make sure you paid attention to the practice problem that we're going to do. So make sure you do those. I believe the lecture participation is due this Friday morning, and the discussion participation will be due Friday evening. I'm sure you all know your project oral presentations, which are the video recordings, are due tonight. And then the memo, is due May 4th. So that's, I believe, the beginning of RR week. And I just wanted to say, I know we've said this a couple times on the project, there's really no wrong answer. We do not expect you to have the same quantitative answers that I got or that any of your classmates got. And in fact, there are so many variables floating around in this project and so many assumptions that you make that it would honestly be kind of suspicious if you did end up with exactly the same answers. And, you know, there are bad assumptions, like if you assumed that one peanut weighs 1 kilogram, you have a problem. But really, there are a lot of different valid assumptions you can make. Where does the water in the inedible part of plants go? Maybe we throw it away, maybe we compost it, and it stays within the system, you know. As long as you explain what you assumed, explain how you're defining your system, you're okay. So really, don't panic about, there are several possible assumptions here, which one's right, unless it's something that is specifically stated in the problem statement of how you're supposed to do it, or if one of your assumptions, you know, makes no sense. But as long as the assumption makes sense and doesn't sort of directly contradict the problem statement, then you're fine. We're really testing your ability to make and justify those assumptions and sort of take a system that's really broad and figure out what assumptions you need to make the system solvable. So yeah, just don't really panic on that. So the last homework assignment, homework 10, is due this coming Monday, and it's on flash drums, which is the material that I'll be talking about in the rest of this video. And then there's one more assignment, homework Z, which is to talk to your faculty advisor. I've underlined faculty, so this isn't like a staff person. It's sort of you should have a faculty advisor within the Department of Chemie who you can talk to. If you're not currently a chemie student, just talk to some faculty mentor in your own department or wherever. but what we really want is for you to document that you sort of had some of those advising conversations with a faculty member. It's not really, we're not picky about the topic of that conversation, so we want you to make this useful for you. So if you have career questions or research questions or anything, we just sort of want you to have that conversation and show us that you did. I know a couple of you have had issues getting your faculty advisor to respond to emails. Welcome to dealing with faculty members. Let us know if you've sort of emailed them a couple times and given them some time to respond and you still haven't heard back. We can help. So yeah, please let us know if you have any questions on homework suite. The only thing to add on assignments is we're going to have a purely optional extra credit assignment due during RRR week, which is for you to, as you're studying for the final exam, generate a problem. So not one that you've copied from this or any other book. Come up with a problem that you think would be fair game for us to ask on the exam. And also generate a solution to that problem. And then we will send all of those problems out to all of you so that you can use those as practice. And if there are good ones, we may select one or two to actually put on the final exam. So that's another incentive of, you may have a problem that you wrote on the final, which presumably would make the final a little easier for you. So just that you don't have to worry about that yet, but just be aware that that's coming down the pipeline and is something that you can brainstorm if you want. And again, it's extra credit, it's totally optional. If it's not something you want to do, you totally don't have to. And then our current plan for the final exam is we will write an exam that will take you 3 hours. So, or, would take us 2 hours or a little less. And so we intend for it to be solvable in 3 hours, but then we'll give you a couple days to do it just so that you can manage your time. And I know there are people who are in different time zones, and so we don't want to make it so you have to take it at some specific time. And remember that Dr. Siston earlier this year sent out, after it was announced that we were doing online learning, sent out the final grade distributions of what final average score you need to get an A, B, and C. So the class is not curved, given that. So you can find that announcement somewhere in your email. So yeah, hopefully that takes some of the stress off the final exam. And we will accept we will post like a PDF or something of the exam online, and you can print it if you have a printer. I don't personally have a printer, so we don't expect you to have a printer. So you can just do your work on paper and send us a scan. So there'll be more information about that coming down the pipeline, but that is currently the plan. Okay, so I think that's everything I have for logistics. So going on to the actual material for this discussion. So what we're studying right now is flash drums. And so what a flash drum is if we have some mixture of A and B, so that could be water and octane was the example from the lecture this morning, but any mixture of two substances. So I've called that stream 1 here, and it has some flow rate of stream 1 and a composition. So here I'm calling the feed composition Z. That's just sort of the convention. We don't want to call it either X or Y because, as you'll see, the other two streams, we call them X and Y. So we're just sort of picking a third letter. But ZA is the mole fraction of stream 1, that is A. And then we go into this flash drum, which is either operating based on increasing the temperature so that some of our components become vapor, or decreasing the pressure so that some of our components become vapor. So we're keeping either pressure or temperature constant and varying the other temperature or pressure. So what we're going to come out with is two streams, a vapor stream, so I'm calling that stream 2 here, which has some flow rate of stream 2, and YA is the mole fraction of that vapor stream that is A. So that's just a convention that we call our vapor mole fraction Y, And stream 3 is also a mixture of A and B. It has some flow rate of stream 3, and it has XA, which is the mole fraction of A in the liquid. Oh, this should say liquid. That is my mistake. I'll fix these slides before I upload them. So hopefully that wasn't too confusing. So yeah, we have a vapor stream and a liquid stream coming out, not two vapor streams. I'm very sorry about that. Yeah, so both, the separation isn't perfect. So both stream 2 and stream 3 will still have A and B, but we are trying to separate A and B. So the vapor stream will be enriched in whatever of the two, A or B, is more volatile. So if we had, say, a 50-50 mixture of A and B in stream 1 and A is more volatile, then the mole fraction of A in stream 2 will be higher than 50%. So A is more volatile, it wants to be a gas, and so the vapor stream will have more A, the feed stream did. Okay. So I'm just going to leave this up for a second so you can absorb that this is liquid, not vapor. Okay. So the diagrams that we use to analyze these systems are called TXY and PXY diagrams. I'm trying to go to the next slide. Okay, so we're trying to figure out what is a TXY diagram, what is a PXY diagram. So I'm showing here an example of a TXY diagram. So our y-axis here is temperature, T, and then our x-axis is mole fractions. So what we have here is xm, ym. So instead of having a mixture of A and B, we have a mixture of M and something else. And so what we have along the x-axis is those mole fractions. And so I'm actually going to move to Notability so that I can color code a little better. Okay. So what we have here is a TXY diagram, so temperature here. And then we have a liquid region, a vapor region, and a liquid vapor equilibrium region. And as you all probably know by now, I really, really hate memorizing things, and this can get really confusing. So all I do is I just think about physically, if I'm increasing temperature, am I more likely to go from liquid to vapor or vapor to liquid? And I hope your intuition is there that, you know, with increasing temperature, we're favoring vapor. So that means this region up here is vapor. And at the lowest temperatures, we're going to have liquid. So this region down here is liquid. And then this sort of region in the middle is vapor liquid equilibrium, which we write VLE. Okay, so how do you read these? What do you do? So the first thing to think about is these mole fractions on the x-axis. So we have a mixture of M and K. So I'm just going to write that here. So when xm or ym, so the mole fraction of M in our system, is 1, then this means we have pure M. And so for pure M, there's no vapor-liquid equilibrium region. We just have one point where we're going from liquid to vapor. So this temperature here is T boil of M. And then when we have a mole fraction of M of 0, then that means over here we have pure K. So this point right here is T boil of K. So if we ask you which is more volatile, M or K, a more volatile thing will become a vapor more easily. And so the boiling point of M is lower than the boiling point of K. So that means M is more volatile. And therefore K is less volatile. So we could just as easily have made this whole graph, instead of xm, ym, we could have our x-axis be xk and yk. And so then we'd have pure K over at xk equals 1, and pure M over on the left at x equals 0, and the whole graph would just be a mirror image. But it would be exactly the same information. Okay, so how do we use this if we're going back to our sort of image of the flash drum that we had earlier, where we have some stream coming in and a vapor stream coming out and a liquid stream coming out. So let's say that our inlet stream had a mole fraction of 0.5. So this is Zm, is our inlet composition, our inlet mole fraction of M. So I'm just going to draw a dashed line so that wherever we are, we can find that Zm really easily. And let's say we heat our system up to, let's say, 70 degrees C. So that means our Zm is here. And what we do is we draw what's called a tie line all the way across our diagram. And where that tie line hits the vapor region, that will be the composition of our vapor stream that comes out. So our Ym will be, what is that, 0.59. And then similarly, where our tie line hits our liquid region, so that's way over here, that will be our Xm. So our Xm in this case is 0.17. So this is really useful. It's really easy for us to read off of a graph. If I had a mixture of M and K that had a mole fraction of M of 50%, or 0.5, and then I heat that mixture up to 70 C, I'll be at vapor equilibrium, and I'll have a vapor phase where my mole fraction of M is 0.59, and a liquid phase where my mole fraction of M is 0.17. But what this doesn't tell us so far is what our ratio of how much vapor do we get, how much liquid do we get. So if I had 100 moles of that original mixture that had 50%, now I know the compositions of my vapor and liquid phase, but I don't know how many moles of each of those mixtures I have. And so that's when we use what's called the lever rule. So the first thing we need to figure out is what is the length of our tie line. So that's this whole length from here all the way to here. And so that's going to be length of tie line (0.59) minus 0.17, which will be 0.42. Okay, and then this is the part that gets a little bit tricky. So what we know, what the rule is that the length of the liquid half of the tie line, so that'd be this part, divided by that total length of the tie line, is equal to what fraction of the feed becomes vapor. So that is a little unintuitive. People want to sort of say, well, the part of the tie line that's closest to the liquid, that's how much is going to become liquid, but it's actually the opposite. So I'm just going to write that down. So length of our liquid arm, so we call that an arm from the Zm to the liquid half, we call that the liquid arm. So it's 0.5 minus 0.17 will get us 0.33. So then our fraction of feed that becomes vapor, so the flow rate of our vapor stream divided by the flow rate of our feed equals the length of our liquid arm, so that's 0.33. Divided by the total length of our tie line, which is 0.42. And you could do the exact same thing with the vapor stream. So the length of the vapor half of the tie line, not half, the length of the vapor arm, which in this case would be 0.59 divided by 0.5, so 0.09, divided by the total length of the tie line is the fraction of our feed stream that becomes liquid. So like I said, this tends to really confuse people because it's not that intuitive. And like I always say, I don't want to memorize things. So I always think of a really simple edge case. So sort of an example that I find easier to think through. So if we take our same feed stream, we have a liquid stream somewhere down here at 0.5 mole fraction. And then what we're going to do is we're going to heat it just barely into the liquid vapor region. So we're going to heat it here to, I'm saying, 63 degrees C. And then if we draw our tie line, we know that our liquid phase is going to be, because we've just barely gone above the point where we're getting any vapor at all, our liquid mole fraction is really close to our initial mole fraction, and our vapor mole fraction is really far away. So that kind of intuitively makes sense to me, is that if my M is more volatile and I have this mixture and I'm just saying like, what's the very first bubble that's going to come out of that liquid? What's its composition going to be? Well, it's going to be mostly M. That sort of feels intuitive to me. And then if I think about what amounts do I expect, well, I expect that vapor stream to be a really small fraction of my flow rate. I've taken this liquid and I've just barely heated it, and so most of my stream is still liquid, and that liquid composition is really close to my initial composition, and I only have this small bubble of sort of really out there different composition. And so that for me helps me justify, okay, what fraction of this stream should be vapor? It should be pretty small, and so that means I want the small half of my tie line, right? So this amount, which is pretty short over the length of the whole tie line, will be what fraction becomes vapor. Okay, so a PXY diagram is exactly the same concept, except now we have our y-axis is pressure or heat. But the x-axis is exactly the same idea. We still have, in this case, it's CCl4 mixed with some other component. And so 1 over here is pure CCl4, and 0 is the pure other component. And we still have this liquid vapor region. The only thing that's different here is we have to think carefully about which region of our PXY diagram is liquid and which is vapor. So what we had before is that at high temperature, vapor was vapor. But at high pressure, it's actually liquid that's vapor. So that should sort of also intuitively make sense to us. If we really increase the pressure on something, we're more likely to vapor. So up top here, we're going to have liquid. Down here, we're going to have vapor. And this middle section will be vapor and liquid equilibrium. But how we use these is going to be exactly the same. So if we have an input feed of a mole fraction of 0.5, we increase the pressure to 0.1 atmospheres, then we're going to end up with vapor-liquid equilibrium. We'll have a vapor stream where the mole fraction is whatever that is. I think it's 0.72, and a liquid stream whose mole fraction is 0.24. And then the fraction of the feed mass or moles that becomes fraction of the feed moles that becomes liquid will be this part of the tie line, so the vapor part of the tie line divided by the total length of the tie line. That's the fraction that becomes liquid, and the fraction that becomes vapor is the part of the liquid part of the tie line divided by the total length of the tie line becomes vapor. So the way that we're using it is exactly the same. The one caution that I would give you is don't try to remember is liquid to the right or to the left. Always think of like up and down. So it's always going to be true that liquid is favored at higher pressure. But if you think about it, I could just as easily have a PXY diagram that goes this other way instead of so it's sort of angling up to the left instead of up to the right. And so now liquid is on the right and vapor is on the left. Whereas over here, liquid is on the left and vapor is on the right. So don't think of left and right because that can change depending on just which component we're plotting for. Think about up and down because in both of these cases, the liquid happens at higher pressure. Okay. So I hope that makes sense just as an overview of what TXY and PXY diagrams are and how we use them. And I've also put on the slide here the rule for the lever rule. So the fraction of the feed that becomes vapor is the length of the liquid arm. So that's the distance between XA, which is the liquid mole fraction, minus ZA, which is our feed mole fraction, and then that's divided by the total length of the tie line, which is going to be XA minus. Okay, so that's how we use TXY and PXY diagrams. And then I just want to do one example problem. It will load here. So this is problem 4.18 from Duncan and Reimer. I'll give you a second to read this. What we have is a mixture of M and K. So this is actually the exact same TXY diagram I was showing before. At 1 atmosphere and 58 degrees C, we're heating it. So we're staying at constant pressure, but we're heating our mixture and going into a flash drum. And then our goal is to get one of the two product streams, so either the vapor or the liquid, to be 50% M, 50% K, and have a flow rate of 100 moles per minute. So your participation question for this lecture or for this discussion section is what is our goal for this stream? So just write any variant of 50% mole fraction from one of the two streams, so something like that, to show me that you watched the video. One note on participation is that last time a few people used this as an option to ask questions also in their submission for the discussion section participation. That's awesome. I totally encourage you to do that. And if I see them, I will respond to them as I'm going through and grading them. So that's awesome. Totally do that if you want to. Really, the point of the participation is just to show me that you are here and paying attention. So if you write anything that shows me that you watched this video, then you get the participation points. But what the question will say is something along the lines of, for the example problem that we solved in discussion, what was our goal? And the goal was to have a stream that is 50% M at a flow rate of 100 moles per minute. I hope that makes sense. Okay. So what we're doing is we're first assuming that this equimolar product, so we're assuming that the stream that has 50% M is the vapor stream, and we're going to answer some questions about it. So what are the possible range of concentrations that could be our feed stream? What's the composition of the other stream, and what's the temperature in the flash drum? And then we're going to answer the same questions, except assuming that it's YM that's 0.5, so it's the liquid that's a 0.5 mole fraction. We're going to answer those same questions. And then we're going to use the lever rule to learn something about flow rates. Okay, so I would encourage you to pause this video and just take a few minutes and try to solve this problem, just to sort of test whether you understood what I just explained about TXY diagrams. And I'll give you a second to pause it. Okay, so hopefully you paused it and solved it and maybe had some questions, maybe got stuck. So I'm gonna go through and solve it. Okay. So this is our question. The text is a little smaller just so I have room to write. Okay, so the first thing we're doing is we're assuming that the equimolar product is the vapor stream. So that means that our vapor mole fraction, Ym, which is in stream 3, is 0.5. So let's first, before we even get started in trying to answer questions, just label what's going on in our TXY diagram. So what we have is increasing temperature favors the vapor. So this is our vapor region up here, and that means this is our liquid region down here, and up in this whole envelope is vapor-liquid equilibrium. Okay, so what the problem is telling us when it says we have Ym of 0.5, that means that we are on that vapor curve at a mole fraction of 0.5. So we can find 0.5 down here and connect it up, and we hit the vapor curve right here, right? So our vapor stream has a mole fraction of 0.5. And then we can draw our tie line all the way over to the liquid region, and we can read that mole fraction off, and we're gonna find that our liquid mole fraction, Xm, equals 0.11, if you read that off the graph. And then, I guess now I've kind of written over it, but we drew our tie line at constant temperature, and if we read the temperature off of the y-axis, our temperature is 72 degrees C. So that, I'm kind of answering these a little bit out of order, but that means our temperature in our flash drum, we can read it right off, and it's 72 degrees C. And what's the composition of stream 4? Well, stream 4 is our liquid phase, and so we already read that off the graph, it's 0.11. And then it's asking what the range of compositions is that's possible in our feed stream. And the answer to that is we just have to be anywhere along this tie line. So that means that our feed stream could be anywhere from 0.11 to 0.5. So the way I think about that is that in order for our lever rule to work, we need to have the center of our level, it's called the fulcrum, somewhere in the middle of our seesaw. We can't have it sort of off on the side. So if we had a feed stream at 0.8, there would be nothing we could do. If we follow that feed stream up, we'll never hit Ym being 0.5. Okay, so that is our first part of the problem. Now we're going to make the opposite assumption. So we're going to assume that it is our liquid stream that has a mole fraction of 0.5, and that, one second. Okay, hi everyone, sorry for the brief pause. My partner got home with groceries and I had to help put them away. So sorry about that. Okay, so back to this problem that we were solving. Basically where we were is we are assuming now that the liquid stream, so stream 4, is the one that has a mole fraction of 0.5. So that means that Xm equals 0.5. And we're gonna ask basically all the same questions we asked before. What is the range of possible feed streams? What's the composition of the vapor stream? And what's the temperature in the flash drum? So what we're gonna do is follow up this exact same 0.5 line that we had before. We're gonna hit our liquid. And so that's what we had been looking for, is our Xm equals 0.5. We're gonna draw our tie line all the way across, and we're gonna hit our vapor composition, which I'm calling about 0.87. One thing to note here is that there's going to be some error. Your answer is going to differ slightly from the answer in the answer key because you read 0.87 and the book read 0.865, we're obviously going to be really lenient about that. So just do your best to read off of the graph as closely as you can. And that's all you really need to do. Okay. So by exactly the same logic that we had before, our permitted range of compositions is anywhere from 0.5 to 0.87. So anywhere in that range, our fulcrum would be somewhere along our tie line. What's the composition of stream 3? Well, that's our vapor phase, and it is 0.87. And then what's the temperature in the flash drum? Well, it's what temperature our tie line is at, and that is 62.5 degrees C. Okay, so now the last thing we need to do is we're going to use our lever rule. So we're asking for what is the flow rate and composition of stream 1, given that our vapor flow rate, so our flow rate in stream 3, is 190. And just remember that we are given that whatever stream is 0.5 has a flow rate of 100 moles per minute. So that means that what we have here is, if we just draw on our PFD that we're given here, our vapor stream is 90 moles per minute with Ym equals 0.87. And our liquid stream is 100 moles per minute with Xm equals 0.5. And what we want to know is what's our flow rate and composition of stream 1. So the flow rate part should be pretty easy. This is just a basic mass balance. If we draw our system boundary around our whole system, our only two streams leaving have flow rates of 190 and 100 moles per minute. We have no reaction going on here, so we can just leave everything in moles per minute. And so we know that stream 1 has a flow rate of 290 moles per minute. So that's part 1. And then we want to know what our composition is. So that's when we have to use our lever rule. So this is a little bit different from how we did it on our previous explanation, because we don't go in knowing what Zm is. So Zm is going to be somewhere in here, and we would like to know, the length of our liquid arm, but we can't do that without knowing what Zm is. So what we do know is that our fraction liquid so that's what fraction of our feed stream becomes liquid, is 100. So that's our flow rate of our liquid stream divided by 290. So that's our total feed rate. And we also know that the length of our total tie line is 0.87 minus 0.5, which is 0.37. So then we know that the length of our vapor arm over the length of our total tie line, so that's 0.37, equals the fraction that becomes liquid, which is 100 over 290. So we can use that to solve for the length of our vapor arm. And so if we just multiply 100 over 290 times 0.37, we get that our vapor arm has a length of 0.127. And then we know where our vapor arm ends. It ends at Ym equals 0.87. So the length of our vapor arm is 0.87 minus Zm. So just remember that Zm is our mole fraction of our feed. So that's the length of our vapor arm. It equals 0.127. And so we can solve for Zm equals 0.74. And we should always do a quick check that that number makes sense. So 0.74, the number that we solved for, better be between 0.5 and 0.87, which was the length of our tie line, and in fact it is. So that's a good sign. So if we want to just sort of tie things up, we can find 0.74 on here, go up, and this is Zm. Okay, So that is everything with this problem. Just going back to the PowerPoint, which as always will be posted. The next slide is just the answers to this problem. And that's all I have for today. I hope this was useful. Please, as always, use Piazza if you have any questions on the homework or on this discussion. Remember to submit the participation assignment for this discussion on bCourses. That assignment will be due, I think I'll make it due Friday evening at 11 p.m. Pacific. And that question will ask, what was our goal stream composition in this question? And we were looking for one of the two streams to have 50% M at a flow rate of 100 moles per minute. And you can also use that to ask any questions. Okay, I hope everyone's doing okay. Please email us, let us know if you have any questions, anything's going on, if you need any help. We'll be really glad to help.